Welcome back. Today we're going to talk about implicit differentiation. This section, we're going to see the consequence of chain rule and the general power rule into equations that are not specifically functions. Let's say we had already discussed notation. So if we see dy over dx, we can say that's y prime. That's one notation. But the question becomes, what if instead of dy over dx, you had d of y squared divided by dx? Means take a derivative of y squared with respect to the variable x. If you think about this as a function, y with the power 2, you can apply the power rule and say, okay, this is 2y to the power 1, right? But since the y is not y and x are two different variables, you can assume that y is a function of x, something like that. Instead of having f of x, we have y of x. That means we are having outside function and inside function. So we have to multiply the derivative of the inside function, which in this case it's y. So the derivative of the inside function is dy over dx. This is the inside function is y. And we apply the power rule. 2y times the derivative of the inside function. Shorter notation, you can write this as 2y dy over dx, or instead of dy over dx, you can choose y prime. Either one is a correct way to say, okay, the derivative of y squared with respect to x is 2y y prime. How about if the function was sine y? Think about it as the way that you assume that this is composition of two functions. What you do is you're applying the chain rule. The derivative of the outside function would be cosine evaluated to y multiplied by the derivative of the inside, which we don't know, so we write d of the inside divided by dx, which you can accept it as this form, or you can go with cosine y times y prime. These two. This would be the derivative. But if they ask you for d over dy of sine y, this means take a derivative of the outside function. It would be cosine y multiplied by derivative of y with respect to y. So dy over dy. dy over dy is simply 1. It's like saying if you have a function f of x equal to x, what would be the derivative with respect to x? It's simply 1. F prime of x would be 1. If you take a derivative of y with respect to y, d of y with respect to y is simply 1. So I want you to see that if the derivative is with respect to x or the derivative which is with respect to y, it's kind of different because you have to apply the chain rule and see that, okay, the derivative of y with respect to x is y prime, but the derivative of y with respect to y is simply 1. This is simply 1. So this is cosine y times 1. Okay, so we're going to use this idea. Why am I talking about this? Is just to see the derivative and tangent line, slope of tangent line for the equations that are not specifically function. A simple example of it is the equation of a circle. The circle is not a function because any vertical line will cross more than once, so this cannot be a function. But still, you can discuss like tangent line at this point. There is a tangent line. Uniquely exists, so there has to be a slope at that point. The question is, what is the slope? If you think about the slope, in definition, it was the derivative of y over dx, or d of f over dx. But in this case, we do not have a function. We say rise over run. We want to estimate the rise over run, which is the change in y divided by change in x. So it would be the derivative along y divided by the derivative along x. You can always think about dy over dx as amount of change in y divided by amount of change in x, but it's an instant, so it will give you the slope. So how do we calculate dy over ax? So let's say given x squared plus y squared equal to 1, how do we find dy over dx? Is you apply the derivative to both sides of the equality. Okay, so I'll say x squared plus y squared equals to 1. This is the equation. So I'm going to take a derivative from both sides. I will say d over dx of left hand side must be equal to d over dx of right hand side. Then calculate what is d over dx of x squared, derivative of x squared with respect to x. So d, let me write it separately so you can see d over dx of x squared plus d over dx of y squared. Since the operation is linear, you can split them and take the derivative of each one separately, and equals to d over dx of 1. So I'm taking the derivative of each term separately since there is addition. Be careful, if it's multiplication, you cannot do this. You have to apply product rule. We will do an example of that as well. So what is the derivative of x squared with respect to x? Derivative of x squared with respect to x, if you apply the power rule, you will get 2x. That is the derivative of x squared, multiply by derivative of the inside, which is the variable x, with respect to d of x. But this is similar to that dy over dy. This is simply 1. I'm going to write in the next line, but I want you to see it's not necessary to always do this. Plus d of y squared over dx would be 2y, multiply by derivative of y with respect to x. On the other side, derivative of 1 with respect to x, derivative of constant, always 0. So what we have is 2x times 1, which doesn't really matter, plus 2y times dy over dx equals 0. So now you have an equation, and what we're trying to find is figure out what is dy over dx. That's what we're looking for. So what I'm going to do is I'm going to move the 2x to the other side and divide by 2y. So what you get is 2y dx dy over dx equals negative 2x. If you subtract negative 2x from both sides, then if you divide both sides by 2y, these two will cancel out. So I found out dy over dx by itself, which is negative x over y. You can cancel out the 2's as well. So this means the slope of the tangent line at any point on this graph, if you pick this point and look at the slope of this tangent line, the slope should be negative x divided by y. But x and y, there are coordinates. So this point, for example, has coordinate of something like 1/2 and 2/3 or something like that. So this would be minus 2/3. This would be 1/2, something like that. It's not exactly these points. So you replace x with negative 2/3, y with 1/2, and it will give you a value for the slope. Hopefully we can, here we do an example of that as well. So the idea is always the same. If you're taking a derivative of an equation that is not a function, you apply this implicit differentiation. This is what we call it, implicit differentiation. I forgot to mention the topic for this section. So we're going to find out dy over dx. Normally, if they want to say evaluate at the point, they draw this vertical line and say evaluate this derivative at the point 1 and 2. So this is the given x and y coordinate. Given 1 and 2, find out the derivative, dy over dx, and evaluate it at the point 1 and 2. So first, our first step is to calculate what is dy over dx. So I'm going to take a derivative of both sides of the equation. What you have is dx cubed. Let me write it step by step. Dx cubed plus y squared minus 5. D over dx of this must be equal to d over dx of, on the other side of the equality, is 0. Left hand side, derivative of x cubed with respect to dx would be 3x squared multiplied by derivative of x, variable x with respect to x. Again, it's not necessary to write this, but I just wanted to see that you can ignore the dx over dx and say this is simply 1. I'm taking the derivative of x cubed, it will be 3x squared, but since the variable is x, I take a derivative of x with respect to x as well. Dx over x is simply 1, so I don't need to write this. How about derivative of x, y squared with respect to x? It would be 2y times derivative of y with respect to x. This is implicit chain rule we're applying chain rule. Derivative of the function multiplied by derivative of the inside value. Minus derivative of 5 is simply 0. On the other side, you have 0. So what we have is 3x squared plus 2y equals, 2y dy over dx equals to 0. So subtract the 3x and divide by 2y. Similar to the last one, you'll get dy over dx equals negative 3x squared and divide by 2y. This would be the derivative. If they ask you to evaluate at 1.1 and 2, so you say d over dx at 1 and 2 is simply replacing 1 for x and 2 for y. You'll get negative 3 times 1 squared divided by 2 times 2, which would be negative 3 over 4. So I found out in this, for this equation, if you look at the point 1 and 2, however the graph looks like, I don't really know how the graph looks like, but however it looks like at point 1 and 2 on the graph, this point belongs to the graph, the slope is negative 3, 4. So negative 3, 4 or something like this. Okay, so that means the graph is tangent like that at this point. The tangent line has slope negative 3 over 4. And maybe the graph is something like this. Or actually going back, since it's not a function. So you have to have multiple points for multiple y values for a specific x value. Okay, more example. Oh, I'm going to use the notation y prime as well, just in case if you see y prime. Sometimes they ask you to find out y prime. So here, this means the same as saying find out what is dy over dx, if x and y are the variables. Okay, so let's try to find the y prime. Take a derivative from the equation, you'll get sine squared of x plus cosine y derivative equals to negative 1 derivative. Just make sure if you're using this notation prime, make sure that you know that you're taking derivative with respect to the variable x. So you should say, okay, what is the derivative of sine squared x? It would be 2 sine x. Chain rule says multiply by the derivative of the inside. Derivative of sine is cosine x. Multiply by the derivative of x, which is simply 1, so we don't write that. Plus derivative of cosine, it's negative sine y. Multiply by chain rule says multiply by the derivative of the inside. Derivative of the inside, dy over dx. Or you could use, instead of dy over dx, you could use y prime. Either one is fine. Since they ask for y prime, I'm going to stick with the notation y prime. Derivative of negative 1, simply 0. So now the question becomes find out what is y prime. I'm going to subtract this 2 sine x cosine x. So what do I get is negative sine y times y prime equals 2 sine x cosine x. So what is y prime? Y prime is simply 2 sine x cosine x divided by negative sine y. This is the y prime. We see it's not super complicated as long as you don't make the mistake. Okay, here's, as we go on, the questions may get complicated. Here's maybe the most difficult one. You'll see that x and y are multiple of each other. So here you will have a multiplication. Given this equation, we want to find out what is y prime. Again, you can take the derivative. I'm going to write this x plus x squared times y minus y squared prime equals derivative on the right side prime. Derivative of x, simply 1. Derivative of x squared y, there is a multiplication, so apply the product rule. It would be x squared derivative I'm going to write it, so it's important to write it so you don't make a mistake. X squared derivative multiplied by y plus x squared times y derivative minus y squared derivative is 2y times y prime. Derivative of y times dy over dx, which is simply y prime. Zero derivative, simply 0. 1 plus derivative of x squared is 2x. Since we're taking derivative with respect to x, there is no x prime necessity. Times y plus x squared times, what is the derivative of y? We don't know. It's still that y prime, because we're looking for y prime. If we knew what the y prime is, we would write it. The y prime, we don't know the derivative. Minus 2y y prime equals to 0. Okay, so now the only derivative left is for this y prime, which is what we're looking for. So we try to move this extra terms to the other side, the one that do not contain y prime. So we have x squared y prime minus 2y y prime equals -1 minus 2xy. How do I solve for y prime? I factor out the y prime. There is x squared minus 2y equals -1 minus 2xy. And finally, if I want to find the y prime by itself, I will simply divide both sides by x squared minus 2xy. Minus 2y, sorry. So you have -1 minus 2xy divided by x squared minus 2y. And I figured out what is y prime. That means I found out what was dy over dx. Okay. Again, you can use the notation y prime or dy over dx, whichever looks easier. Use that, stick with that format. They ask you for y prime, it means they want dy over dx. If they ask you for dy over dx, it's the same as y prime. If there is multiplication, make sure that you apply the product rule and do it step by step so you do not miss an extra y prime or dy over dx or something like that. Okay, here I haven't wrote what we're looking for. So here, by the way, we can extend this to find higher derivative. So let's try second derivative. It's going to be more work, but it's still possible. So before I go, I mentioned this. Maybe I should mention that if you're given y prime and I ask you find out what is the derivative, you can write this as y double prime, because you're taking the derivative of y prime, which is the second derivative. This means if they ask you to find out dy over dx of y prime, it's the same as saying taking out the derivative of y prime, which is the second derivative. So to find the second derivative, first you need to find the first derivative, then take a derivative of that one more time. That's what you would do for the function, the same for the equation. So let's find the first derivative first. You'll have x to the fourth derivative plus y to the fourth derivative equals to 1 derivative. X to the fourth derivative is 4x cubed plus y to the fourth derivative is 4y cubed multiplied by the derivative of y prime equals to 0. So what is y prime? You can move these terms to the other side. You get, let me write it step by step again. Make sure everyone follows steps. I subtract the 4x cubed, then I divide by 4y cubed. So you get y prime equals -4x cubed divided by 4y cubed. You can cancel out the 4's, so simply y prime becomes -x cubed over y cubed. We found out y prime. So if you want to find the second derivative, so you take another derivative from this equation. That means you say take a derivative of y prime equals to the derivative of the right hand side. X cubed divided by y cubed derivative. This is a good example for quotient as well, so you can see the quotient derivative. The left hand side derivative of y prime means the second derivative. You take another derivative from y prime, it means the second derivative. And right hand side, apply the quotient rule. Derivative of numerator, -x cubed derivative times the denominator, y cube, and minus negative x cube times derivative of the denominator, y cube derivative, all divided by denominator squared, y cube squared. So I'm going to keep it as y derivative, second derivative. Okay, derivative of negative x cube, negative 3x squared times y cube, minus minus becomes plus x cube times derivative of y cube. Be careful not to forget that there is a y prime here. 3y squared times y prime, and denominator y to the 6. Y cube squared is y to the 6. Okay, you might say, okay, I found the second derivative. But the second derivative involves the first derivative. So somehow I should have only x and y, not anything in terms of y prime. So what do? I already have y prime. What is y prime? It's negative x cubed divided by y cubed. So I replace it into the equation. I'll say, okay, the second derivative is basically everything is there. Negative 3x squared times y cubed plus x cubed times, let me put the 3 up front. Constant first is always a better notation. Y squared times, instead of y prime, we replace negative x cubed divided by y cubed. Right, we have y prime as negative x cubed divided by y cubed, and divided by y to the 6. This should be the second derivative. There is no more derivative involved on the right hand side. But you can simplify always. You can cancel out 2 of these with 2 of that. So you can say y double prime equals, and there is an extra y here. So to get rid of it, what do? I'm going to multiply a y in the numerator everywhere. And the same, I'll multiply in the denominator. It's like if you have 2 over 5, you multiply 2 here. Sorry, you multiply 3 here and 3 here. It doesn't change the ratio as long as you do it to both numerator and denominator. I multiply a y everywhere, so I can cancel out these 2 as well. So what you get is negative 3x squared, y cubed times y becomes y to the 4th, plus actually there is a negative sign here, so I can say minus 3x cubed times x cubed becomes x to the 6th, and there is no y. The y is cancelled now. And the denominator is simply y to the 7. This is the simplified version of the second derivative. There are stuff in the numerator that you can factor, but it doesn't make it that simpler. Okay, so if they ask you for second derivative or even third derivative, you have to apply quotient rule again over and over. It's nothing complicated as long as you make sure that you using the chain rule. Yeah, I'm imposing the chain rule on these derivatives. If you're dealing with something like, right, maybe sine of cosine of y, and they ask you to find the derivative of this with respect to x. This means apply the chain rule first. You say sine derivative at cosine y times the derivative of the inside, cosine y derivative. Sine derivative is cosine of cosine y. Again, this is not multiplication. This is operating. Sine operates on this function. If it was multiplication, you should apply product rule. So we have cosine of cosine y multiplied by the derivative of cosine y. Again, you should apply chain rule. Derivative of cosine at y multiplied by derivative of the inside, y prime. This y prime is very important. If you don't write it, then you don't have the equation correctly. You don't have the derivative correctly. Cosine y times negative sine y and multiply by y prime. It's not any different. If the more complex the equation becomes, the more you have to break it up into pieces and pieces. I think these are good examples. Anything else is very similar to these. Try to do your homeworks and again pick Pick one of these two ways to write it, either one that looks simpler to you and you see that you make less mistakes. Try to stick with one way. This dy over dx is a better notation than y prime, because later on when we discuss rate of change, you might need this dy over dx. Okay, I'm gonna stop at this point.